So Mod 2 is all about exponential functions. We're going to look at the inverse of exponential functions as well. Remember, we couldn't write an equation for an inverse exponential function, so we'll start talking about that next week. All right, but that's where we're kind of starting today. So first, an exponential function, that is a function in which the variable is an exponent. That's how we would define an exponential function. So down here we have general form of exponential function written. It's like a times b to the x power. And the exponent happens to be the variable, happens to be the x. A and b are both constant terms. If we start with just the letter A, in these two equations here, it could be y equals a times b to the x, or in function notation, f of x equals a times b to the x. A is the leading coefficient. That's what we'll always refer to as the leading coefficient. And in quadratics, we also called that the leading coefficient. It happened to be the variable a, or it happened to be the constant of a as well. All right, and we want to say the leading coefficient does not equal 0. That's really important. Okay, and then
Does not?
I'm sorry?
It does not equal 0?
A cannot equal 0, because if a equals 0, you're just going to get 0 times something, and anything times 0 is just going to be 0.
Mm-hmm.
So we never want a to be a value of 0. It can be negative numbers, it can be positive numbers, but it can't be 0. And actually the sign of a is important as well. So the sign, whether it's positive or negative, that affects which side of the x-axis the graph occupies. Okay, so that's the sign which affects the x-axis of which side the graph occupies. Okay, so that means if the sign's negative, the graph will usually be below the x-axis. If the graph is positive, then if the sign is positive, the graph is usually above the x-axis. And we'll talk about that in a minute here as well when we look at an actual graph of it. The last variable we have is the b value. And b, this is called the growth factor. I guess it depends on, let's clarify, because it could be the growth or decay factor, but when b is greater than 1 specifically, we'll say it's called the growth factor. So you might hear of exponential growth. You've probably heard that term before. That's what that means. There's another situation where b equals 1, and when b equals 1, it's not really an exponential function. So we don't like it when b equals 1. That would just become a constant function. Okay. So when b equals 1, it's not really an exponential function, it's more like a constant function. If b is between 0 and 1, so it's a decimal or a fraction, like 3/5 is a number between 0 and 1, that's when it's called the decay factor. And that's when you would deal with exponential decay. And then the last one, if b is less than 0, it won't work as an exponential function. Let's take a look at an example of what I mean by that. So like, let's say if b equals -2. So you would say y equals -2 to the x power, something like that. Well, what happens here is if x equals 1, then you get -2 to the first power, which is -2. If x equals 2, you get -2 to the second power, and then you get -2 times -2, which gives you a +4. If x equals 3, then you get -2 to the third power, and you'd get -8. So what happens if b is less than 0, which means it's a negative number, you're going to keep going negative, positive, negative, positive, negative, positive. It's going to flip back and forth. So it doesn't create an exponential function anymore. So that's the idea. Okay, so that's just the general idea for why b is less than 0. Okay, now we're going to look at just an exponential function. This is what they generally look like. There's two examples here. The first one is showing exponential growth. So exponential growth right here. This is the graph of y equals b to the x, so it's just assuming that a is 1. We'll start with that. A equals 1, so that's why it's not written down. All right, so this is like a parent function for these types of graphs. And this is when b is greater than 1. So that's where exponential growth comes in. All right, the first thing I want to point out is that there's an arrow right here which is pointing out the asymptote. Okay, and the asymptote would be the line y equals 0. In this case, there's always going to be a horizontal asymptote on these types of problems for exponential functions. Okay. And then we see 2 points here. One of them is 0, 1, one of them is 1, b. And that's just like if we created an actual XY table and plugged in 0 for x, you would get b to the 0 power. So you'd get 1. Anything to the 0 power is 1. If you plugged in 1, you'd get b to the first power, and b to the first power would just be b. That's where those two values come in there. All right, so hopefully so far that's not too crazy for us, but that's the idea for exponential growth. And it's always going to have an asymptote on the left side for exponential growth. I should say the function approaches, we're going to talk more about asymptotes. On the left side. So what I mean by that is if we're going from left to right, we see that's really close to the asymptote. And then this function just kind of explodes in an upward direction. That's what I mean by it approaches the asymptote from the left side. We'll put an arrow on that too because it goes infinitely in both directions. But on one side, it's just getting super, super close to the asymptote. Something else that could happen is we could have a equals -1. So this looks like y equals negative times b to the x. And that would be -1. And in that case, the function's going to come through here and explode in the other direction. You're still going to have the point 0 comma -1 instead, and you're going to have the point 1 comma -b. And it just goes in the opposite direction, but that is still exponential growth, even if a equals -1. So some people get confused because they see a negative number and they think, oh, exponential decay because it's a negative. No, exponential decay happens based on the b value. If the b value is between 0 and 1, that's exponential decay. So you could have positive growth and you could have negative growth that's growing in a negative direction. Or you could have exponential decay, which is going to have an asymptote y equals 0. And this time, notice that the function approaches the asymptote on the right. So I always think about graphs kind of like stories where we start on the left-hand side when we're reading a book and we move to the right-hand side. So the same thing's happening here. Going from the left to right, it starts in this really big growth area and then it shrinks down and ends up approaching the asymptote as it gets to the right. So the function approaches the asymptote on the right. That's the idea for this particular problem. And then the definition of an asymptote real quick, just in case we're not 100% familiar. That's a line that the graph approaches more and more closely. But it never touches. So just to clarify, it's possible that your function could go through an asymptote, like kind of in the middle, but on the end behavior, when we're looking at the far end, it's never going to touch the asymptote. It's going to just get infinitely close to it. So the asymptote kind of prevents it from going across this 0 line as it goes out further and further. All right, that's what asymptotes do. And you could also have negative growth here, which would be, or negative decay, which is the function is coming up from a negative direction. And then ends over here. So you'd have 0 comma 1 and 1 comma negative b. Or 0 comma -1, sorry. And then 1 comma negative b. And that would be the same thing if y equals negative b to the x. That's assuming a equals -1. So you could have negative growth or negative decay as well. All right, just kind of a weird way to think about it, but It's just the function coming from the negative direction and then approaching the asymptote. That would show negative decay. All right, so that's just the quick introduction to exponential functions. Now what we're going to be doing today is we're going to practice graphing these types of functions. So all exponential functions that we're going to deal with are going to be translations of these two graphs, which means we move the asymptote and we move where it's going, and then we might move the function up or down, or we might move the function left or right. That's what we're really going to be looking at today. When we are sketching these types of functions, these are the steps I want you to follow. I want you to be able to find 4 points to fill in the table. So 4 points only, that's what you need. Excuse me. Hopefully we can deal with integer values as much as possible. Sometimes we might not be able to. Excuse me. I want you to draw an axis and set an appropriate scale for the function. Always important to draw an axis and set the appropriate scale. We're going to identify the situation as either growth or decay. Is this exponential growth or is this exponential decay? And then finally, we're going to state the domain and range. So we'll talk about domain and range of these types of functions, what to expect. So first thing I want to do with any one of these functions is take a look at the b value. I'm going to start with this one right here. Identify growth or decay. So for example, number 1, the b value is a positive 3. Is that number between 0 and 1, or is that bigger than 1? That's what we want to ask. Well, yeah, this one's bigger than 1, so that's growth. So b is greater than 1, so that means it's going to be moving away from the asymptote when we graph it. So that's the first thing I want to do. Like, hey, that's really easy. I can identify growth and decay. So if it's easier for you to do it visually once you see the graph, that's perfectly fine. But hopefully, ultimately, we can start identifying them right away. The next one's 0.4. Growth or decay? Decay. The b value is between 0 and 1. All right, we don't care about the negative in front. The negative is not determining whether it's growth or decay. This time the b value is between 0 and 1, so this is decay. And that means from left to right, it's moving toward the asymptote as we move from left to right. Okay, so that's the first thing I do with those two examples. The next part, I'll go back up and say, let's find 4 points to define the table, to fill in the table. So typically I'd want to say, like, let's try and stick to some easy points, like maybe, I see this as x plus 2 here. So if I wanted to deal with like a 0, I'll just say, let's start with x equals -2. And then -1, 0, 1, 2. Maybe those will be my 4 points. Or actually even 5 points. We'll just go 0, 1. And when I use -2, that means I just plug in -2 to the function. -2 plus 2. And I started with -2 because that just gives me 3 to the 0 power. Anything to the 0 power is 1. So I get 1 minus 5. I got -4 for my y value. My input's -2, my output becomes -4. I plug in -1, and I'm going to get 3 to the first power. 3 to the first power is just 3, so 3 minus 5 is -2. Plug in 0 and I get 3 squared. 3 squared is 9. 9 minus 5 is 4. Plug in 1 and I get 3 to the third, which is 27. 27 minus 5 is 22. So I just came up with 4 points there. Now, to sketch my graph, I need to figure out where I want to put this. So I know where I need to put my axes. So I see like I have a -4 here. I have a -5 here. So that's going to help me determine where I want to set my graph too, is paying attention to this -5 right here. So I'll go ahead and put the center of my axes right down the middle here, the y-axis right down the middle. And then the x-axis, I'll go up a few lines like this. And I'll count the x-axis by 2s, 2, 4, 6, 8, whoops, 10, 12, 14, 16, and then I would get 18 up here at the top. And then down this way, -2, -4, -6 by the time I get down there. And then the y-axis, I'll probably just count by ones. 1, 2, 3, or the x-axis, I mean, 4, 5, 6. 1, 2, -3, 4, 5, 6. So -6. Okay, that's kind of where I want to set my axes. And the reason I want to do that is because I'm going to have an asymptote on here. There's always an asymptote for exponential functions. And this is where the asymptote's going to be y equals -5. That's not a coincidence. It happens to be that value right there. Whatever number's added or subtracted on at the very end is always going to be where your horizontal asymptote is. So in this case, y equals -5 happens to be my asymptote. If I plugged in x equals -3, I'm going to get like 4 1/4, -4 1/4. If I plug in -4, I'll get like -4 1/2. I'll keep getting numbers that get closer and closer to that -5, but they never cross the -5. The same thing's going to happen on the second problem. I can see right up here, it's +2. So I know the equation of my asymptote is going to be y equals 2. Without even graphing it, I can tell where the asymptote is going to be based on that last number. So last number always determines the asymptote. That's super, super important. Now to go ahead and sketch my graph, I'll go ahead and put -2, -4 on there, -1, -2, and then 0, 4, 1, 22 is unfortunately going to be off my paper. So I didn't do a great, like honestly I tried to do it, I didn't even do a great job of scaling this because I didn't get all 4 of my points on the paper. So it might not be a bad idea to say, let's do a -3 and then put that on there, and then I'll have 4 points that are on my graph to actually represent my graph. So, oops. And honestly, I didn't even do a good job of sketching it because I know it doesn't cross 1 before it leaves the graph, so it should look something like this and never cross that line at y equals 1 because of the way my scale's set up. So I could plot the point -3 here and, like I said, find a -3 instead. And that's going to make this, what is it, 3 to the -1. And whenever we have a negative exponent, it really just becomes 1/3 to the first. So I'm really getting -4 1/3. So -4.3 would be where that would be at -3. Okay, so it never gets below that 5. That's what's going to happen when I have this asymptote. Okay, so that's the idea for problem 1 there. The last part, identifying domain and range. One of the nice things about these functions is domain for any exponential function is always going to be all real numbers, -infinity to +infinity. All x values should work. I can plug in whatever I want for x, negative, positive, 0, doesn't matter. Okay. The range is going to be a little trickier. There's an asymptote here that kind of keeps my function in line. I can never go below the number -5, but I can go up to +infinity. And again, that -5, that's represented in the equation up top. Okay. So in this case, I just want to point out it's parentheses, not a bracket. So we did a lot of brackets with quadratic functions. And it's parentheses because -5, because the function can't touch the asymptote. So -5 is not included. So we can't touch the asymptote, so it's not included. So that's really important to make a note there. That in these functions, we're never going to include the asymptote. We always do a parentheses to open to represent that this function looks good. To represent that this function can't touch that value. The range of the second function, I know the asymptote is y equals 2. So it's pretty safe to say, oh, the range is going to be from 2 to infinity. That's a good safe bet. And then we can go ahead and try and sketch it. And say this goes from +2 to +infinity from there. Now, if I plug in some points, I'll do -1 here. Again, just seeing here that there's -1, so it'd make it -0.4. It'd be 0.4 to the -2 power to squared. And I'm just going to plug it in my calculator. I end up getting -4.25. I did this a little earlier, so I have these values already. Plug in 0, and I'm going to get -0.5. Plug in 1, and I get 1. Plug in 2, and I get 1.6. Now, I just want to point something out here real quick. Look at these y values. Whoops. -4.25, -0.5, 1, 1.6. Those values are all less than 2. So look at my range. My range is saying that the values go from 2 up to +infinity. But it turns out I have the incorrect domain here, or the incorrect range here. That is not right at all. Okay. Because it turns out 2 is the asymptote, but what's happening this time? Because of the negative, it's coming from a negative direction. Because of this negative number right here, it's coming from a negative direction, and it's ending at 2. So it turns out that the range is actually from -infinity to +2. It ends at 2 still, just goes the opposite direction. So that's how range works. You have to just kind of think about it logically. Am I including these numbers or am I not including these numbers? So now I'm including all of the numbers up until 2. I'm going to sketch this one. I'll probably do this one right in the center. And then I want to include +2 as my asymptote. So if I count the y's by 1s and then get up to 2 there, I can put my asymptote right here at the top of my paper. And say there's y equals 2. It's never going to go above that line. I'll go ahead and count the y-axis by -1s. And I'm going to count my x-axis by 1s. 1, 2, 3, 4, 5, 6. 7. Okay. And then -5 over there. And then the last part, I'll plot my points. -1, -4.25. So somewhere over here. 0, 1/2. 1, 1. 2, 1.6. And then we'll see this function gets super close to that asymptote. It's decay, so it's going to end at the asymptote on the right-hand side, but it'll never touch it. All right, so I just plugged these values into my calculator, and then I was able to sketch the graph. So the keys here for you guys, make sure you can identify the domain and range correctly, and then make sure you can sketch the graph accurately and create a scale that works for you. Your graph does not need to look exactly like mine, but you want to create a scale that uses all 4 points. On the left side, I wasn't able to get all 4 points on my graph, so I added another point, so that way I could say, hey, I have 4 points that are all on the graph. Okay, so that's perfectly fine to do. All right, so now I've got two examples that I want you guys to try, 3 and 4. Excuse me. I'd say start by identifying if they're growth or decay, and then go ahead and find 4 points and see if you can sketch them. Feel free to use Desmos if you want to. That's perfectly fine. Or use a graphing calculator, whatever helps you best. Ask me questions if you're stuck on anything at all. Let me know what you need help with. All right, so I got the answers up here so you guys can take a look at them now.